In solving integrals that involve rational functions like this one, there are a few different techniques that we need to pull together. Our main focus for this section of the textbook is the technique of partial fraction decomposition. But before we can use that, we need to talk about a preliminary technique that is sometimes necessary for some rational functions. In this example, we have the integral of the function 2x cubed minus 14x squared plus 29x minus 9, that whole polynomial, all divided by x minus 3 times dx. So we're integrating a rational function here, a ratio of two polynomials. And in our last video, we talked about what kinds of rational functions do we already know how to integrate. And it turns out that all of those rational functions had something in common. It turned out that in each of those cases, the degree of the polynomial on top was always less than the degree of the polynomial on the bottom. And that's a key property that we need in order to be able to integrate rational functions successfully. The problem is that we will frequently encounter rational functions in which the degree on the top is not less than the degree on the bottom, such as in this case, the degree on the top is 3, the degree on the bottom is 1. So what can we do? Well, first, let's look at some definitions. So here are some definitions. A rational function is considered a proper rational function if the degree of the polynomial on top is less than the degree on the bottom. So for example, we could have 4x squared minus 7x plus 8 over 9x cubed plus 6. The polynomial on top has degree 2, the one on the bottom has degree 3. So the top has a lower degree than the bottom. That is a proper rational function. And a rational function is called improper if the degree of the top is greater than or equal to the degree of the bottom. So for example, in our first example here, 6x squared minus pi over 7x squared plus 3x minus 1, both the top and the bottom have degree 2. So that is improper. In the other example, x to the 7th plus 5x to the 5th plus 3 over x to the 4th plus 19, the degree on the top is greater than the degree on the bottom. In either case, that rational function is improper. So let's examine the integral that we're trying to solve using these definitions. The problem that we have here is that this rational function is an improper rational function. The idea of proper and improper rational functions kind of is the same idea as proper versus improper fractions. A proper fraction is one in which the top is smaller than the bottom, and an improper fraction is one in which the top is greater than or equal to the bottom. It's the same kind of idea here. This is an improper rational function. And we're not going to be able to find the integral of this thing as it is. But here's a fact. Any improper rational function can always be written in the following form. We can always break this down and write it as a sum of a polynomial plus a proper rational function. So we can take any improper rational function and write it in this form as a sum of a polynomial and a proper rational function. Now, polynomials we know how to integrate. They're always easy to integrate. Proper rational functions, we don't know how to integrate every single one of them yet, but we do know how to integrate quite a list of them, the list that we looked at in the last video. So hopefully, if we can break this down, we'll end up with a sum where both components of that sum, both terms of the sum, are things we know how to integrate. But how should we go about doing this? The way that we're going to do this is to use long division. So first, let's go back and remind ourselves how long division works for numbers, for integers. Let's take an example here. Here's an improper fraction, 893 divided by 7. Of course, a fraction is the same thing as a division problem, right? we should be able to write this as an integer plus a proper fraction, that is something over 7. Now the problem is you can plug this into your calculator, take 893 divided by 7, and you will get an integer followed by a decimal point and lots of decimal places. That's not what we want here. We don't want a decimal expansion. We want to just have a fraction after the integer. So how do we do this? We can do long division. And you learned how to do this in grade school. You might have forgotten, but it's a very simple algorithm. And it's important to think about how that algorithm is actually working. So let's just do this as an example here. We are looking for 893 divided by 7. And let's just make sure that we're thinking about how this algorithm works as we're following the process here. You should never follow an algorithm without understanding where that algorithm comes from. So if I want to divide a number by 7, that means really what I want to do is I want to subtract 7 from that number over and over and over again until I can no longer subtract 7, and I want to count how many times I subtracted 7. That will tell me how many times 7 goes into that number. So long division is just a way of allowing us to subtract multiples of 7 from 893 in a way that lets us keep track of how many multiples of 7 we've actually subtracted at any one time. The first question is, how many times does 7 go into 8? Well, it goes in 1 time. Now really, that's not an 8, it's an 800. So 7 goes into 800 about 100 times, but we'll get to the rest of the digits later on. And now we'll just say, all right, 7 times 1 is 7. So the multiple of 7 that we're subtracting is actually 700, but since we're only in the hundreds place, we're not going to put the other digits. We can subtract this, and we will get 8 minus 7 is 1. So there's 1 left. Now we can bring that 9 down. That 1 is actually a placeholder for 100, and the 9 is actually standing for 90, so we actually have 190. But we can treat it as a 19. So how many times does 7 go into 19? Well, I know that 7 times 2 is 14, so 7 goes into 19 twice. I'll put a 2 up here. And then 2 times 7 is 14. So I'll subtract the 14 from the 19 and see what I get, and I get 5. Now I can bring that 3 down. And how many times does 7 go into 53? Well, it goes in 7 times. And 7 times 7 is 49. So I can subtract 49 from 53 and get 4. There's no other digits to bring down, and 4 is less than 7. So we're done. That 4 is the remainder. But really, what we'd like to say then is that 893 sevenths is equal to 127 plus 4 sevenths. And you can check that by converting this mixed number back into an improper fraction. You could take 127 and multiply it by 7 to get a fraction and add the 4 sevenths to that, and you get 893 over 7. So our long division has allowed us to subtract multiples of 7 from that top number, from the dividend, and count how many multiples of 7 we actually subtracted and what was left over when we could no longer subtract multiples of 7. That's how long division works. So let's try and apply this to polynomials instead of integers. This time, here's the rational function that we started with that was inside our integral. 2x cubed minus 14x squared plus 29x minus 9, all divided by x minus 3. We'd like to write this as a polynomial plus a proper rational function. And long division will let us do this. So let's set up our long division problem the same way that we would if we were using integers here. I want to take the number on top, the polynomial on top, that is 2x cubed minus 14x squared. Now be careful here. If you have a long polynomial with lots of terms, there may be some powers of x that are missing sometimes, and you should always incorporate that in there. So in this case, I have an x cubed and an x squared, x to the first, and a constant term. So there's nothing missing. But if there was something missing, you'd want to insert that in with a 0 coefficient. Don't need to do that here, but that's okay. This is plus 29x minus 9. Okay, we're dividing this by x minus 3. So let's get started. When you're doing polynomial long division, what you should do is you should look at the highest degree term that remains in your dividend, right here, 2x cubed, and look at the highest degree term that is in your divisor, in this case, x. The question is, how many times does x go into 2x cubed? Now, how many times is kind of not the right question to ask here. What we really should ask is, what can I multiply by x to get 2x cubed? And the answer is, well, if I multiply 2x squared by x, I will get 2x cubed. So our next step in long division is to multiply whatever number we just got by the divisor. So let's say 2x squared times the entire divisor. So 2x squared times x is 2x cubed as planned. And then 2x squared times negative 3 is minus 6x squared. Notice that that lines up with the next term over in our dividend. Now we're going to subtract this entire polynomial from the one above. So be careful, watch out for those coefficients. 2x cubed minus 2x cubed is 0, which is to be expected. Negative 14x squared minus negative 6x squared really means I can change this to a plus, put that negative there, and make this a plus. So really it's negative 14x squared plus 6x squared. That's going to give us negative 8x squared. So now we can bring our next term in our polynomial down. This is plus 29x. This is just like bringing your next digit in your long division problem down. So now we can ignore that first term of 0 there, and we now have a first term of negative 8x squared here in our dividend. And the question is, how many times does x go into negative 8x squared? And the answer is, I need to multiply x by negative 8x to get negative 8x squared. Don't forget that negative there. It's going to be negative sometimes. So I can multiply x, which is the first term of my divisor, by negative 8x, and that gives me my first term of my dividend that remains. Let's multiply negative 8x times the entire divisor now. So negative 8x times x is negative 8x squared. And negative 8x times negative 3 is positive 24x. And we are now subtracting this entire polynomial here, negative 8x squared plus 24x. We're subtracting that whole thing from the polynomial above. So do put it in parentheses and put a minus sign in front of it. So negative 8x squared minus negative 8x squared, they cancel out. We have a 0 here. And 29x minus 24x is going to give us a positive 5x. And now we can bring our negative 9 down. And for the last time, let's ask, how many times does x go into our first remaining term here, which is 5x? Or what can I multiply by x to get 5x? Well, that's easy. I just multiply x by positive 5. So I'll put a plus 5 up top. And now again, let's multiply 5 by our entire divisor. 5 times x is 5x. And 5 times negative 3 is negative 15. And we are subtracting the entire expression, 5x minus 15, from 5x minus 9. So the 5x's cancel. And again, this is a little confusing here. I'm going to change that negative to a plus and a plus here just to put that minus sign in. So negative 9 plus 15 gives us a positive 6. Now, 6 has a lower degree than our divisor of x minus 3. So x minus 3 can't go into 6 at all. That means that 6 is our remainder. Don't forget that in polynomial long division, your remainder might be positive or negative, or it could be 0 in some cases. Sometimes it might even be a polynomial. If your divisor has a degree higher than 1, then the remainder will be whatever you end up with that has a degree less than the divisor. So if your divisor has degree 2, your remainder might actually be degree 1 and might actually have an x in it. All that matters is that you end up with a remainder that you cannot divide x evenly into that at all. So let's now rewrite our rational function as a polynomial plus a proper rational function. The polynomial is what we just got on the top here. That is 2x squared minus 8x plus 5. And our remainder was 6, so our proper rational function that remains is plus 6 over the denominator that we already had, which is x minus 3. So this is exactly equal to our original rational function, but now it's in a form that we should be able to integrate. In fact, if you look at this carefully, you realize, yes, this is equal to the original rational function. You can check that by multiplying the polynomial part by x minus 3 and putting it over x minus 3. In other words, get a common denominator and add them all together, and you'll see that it does actually match up with the original. But now it's in a form that we actually can integrate every term of this new expression. So let's come back to our problem. We needed to rewrite our integrand using algebra in some form that's equal to the original, but that we know how to integrate. And we've now done that. We know that our integrand is equal to 2x squared minus 8x plus 5 plus 6 over x minus 3. And we have this integral of this expression, all of it times dx. So the algebra was the hard part. We just need to finish the integral now, and the integral is easy. Let's do this. We can integrate each term of the polynomial very easily. What's the antiderivative of 2x squared? Well, it's going to be x cubed over 3, so that's actually 2/3 x cubed. Minus, well, antiderivative of 8x, we're going to raise the power. We're going to have x squared times 8, but divided by 2, that's 4, plus 5x, plus that last part there, 6 over x minus 3. That is an integrand. That is a function that you could use u substitution for. You let your u be the denominator, which is x minus 3. But in our last video, we talked about how we can solve any integral of any rational function of that form, a constant divided by a linear function. It will always work out the same way. It's going to end up being that constant on the top, 6, times the natural log of the absolute value of the denominator, x minus 3. And you'll have to divide by the coefficient on the x. That's a consequence of that u substitution that you do. However, the coefficient on the x here is 1, so divided by 1 doesn't do anything, so I'll just leave it this way. 6 times the natural log of the absolute value of x minus 3. And of course, it's an indefinite integral, so we have to add a constant. And we are done. This is the integral of our original rational function. The integral was the easy part, the algebra was the only hard part.